Students, today we will be talking about MEMS, scanning macrometer. In short, SMM. Now these are basically used in these are mainly their role is to mainly steer and reflect the incident light. And they do it by the angular rotation of the mirror. Now their application are in the field of optical MEMS, barcode scanning, digital light projector, optical switch, adaptive optics, and confocal microscopes. Now the principle that they use that is being used in scanning macrometer, it is called electrostatic actuation. Or EA. Now this EA are the electrostatic forces. So when describing this electrostatic actuation, what we have to do, we have to consider the electrostatic forces between parallel, movable and flexible electrodes. So there are two electrodes which are parallel to each other. They are fixed, they don't move relative to each other, parallel to each other, and they can slant. They are movable. So between a pair of movable fixed electrodes, they are also parallel plate type. And the size is up to 2 millimeter for smaller dimension. So what you have here is a fixed electrode like this, sorry, a moving electrode, and we have two fixed electrodes. So these are the fixed ones and this is the moving one. larger mirror diameter, say by large it is greater than 2 millimeters, then the scan angle, with this scan angle, because it's not that all the scan angle will be always 0 degree, it can be changed also. The scan angle, it actually leads to a large gap between electrodes. It's very easy to understand. Suppose these are the two electrodes. If one of the angles on the electrode moves with a certain angle theta, so a large gap is produced between electrodes, and this large gap will actually cause increase in drive force. And this can be used in bulky driving conditions. Now that means we call it as a Vdrive, or whatever potential or force related to this increasing angle. Now this angle or this voltage, or whatever you may call it, as potential, has to be decreased. Okay. Now, Vdrive, this needs to be lowered down for effective performance, and to do that, what can be done is, if we use, instead of using torsion springs in MEMS, we can replace it by something called a comb. Right, so we have something like this, torsion spring, something like this. And then the resonant frequency can be studied by comb on pull down voltage, by comb on pull down voltage. Now the performance of a scanning mirror, performance of an SMM, it depends upon certain factors like the scan angle, then it will also depend upon the resonant frequency, then the resolution, the driving voltage, and the surface quality. Now let us try to understand the basic structure of an SMM. So what we have here is a frame on which the system sits. There is an inner comb and there is an outer comb. So this one stands for the inner comb, and This one here is the outer comb. And this is the frame. Now many times it is required that we deposit an oxide layer, especially when making devices like transistors. Now whenever we are putting an oxide layer, there will be a thickness associated with that oxide layer. Now, so oxide layer, with thickness is varied. It is varied. Then it will create a pull-in voltage. So there are basically two types of voltages when dealing with common is pull-in and pull-out. So this particular phenomena will cause a pull-in voltage of about 450 volts. Now most of the biaxial mirrors are usually found in something called a gimbal combination. So what happens in this gimbal combination is the mirror is attached to the frame through inner torsion strings. Whereas again this inner frame is again attached to the outer frame by torsion strings. By torsion springs, not strings. Now the device is actuated using 4 electrodes. So device is actuated using 4 electrodes. 2 are placed under the inner comb and 2 under outer comb. So 2 under inner comb and 2 under outer comb. Now the rotation, as we have already said that we are dealing with mirrors and their rotation, therefore the maximum rotation possible or the maximum rotation angle is, we call it as theta max, and it is equal to Tf plus Tc by Lf Tx by Tox. Tf is of the upper layer of the film, thickness of the film, TOX is the thickness of the oxide layer, and LF is basically the finger length. It is the distance between the moving part and rotation axis. That is distance between moving part and rotation axis. Now there is a parameter called shock impact reliability. And it is mainly used in to analyze the automotive, mainly used in automotive and aerospace applications. And operating in the hard conditions. So vehicles operating in automotive and aerospace application in hard environments, they actually undergo this shock impact reliability test. Now, so basically they provide the material as shock and they see how the material responds. Now coming to considering these, there are a few few